So good afternoon everyone, and welcome to the last session of the day. I'm actually glad that it's the last session of the day because we might overrun a little bit. If you've been to some of my presentations before, you tend to know that I just talk too much. And I hate demos because I always fail, but I actually have some demos, so please pray for me so we won't have any problems. So my name is Victor Isakov. I'm based in Sydney, Australia. So I've been doing a lot with SQL Server since version 6. We're not really here to listen to me talk about myself, so I won't. So there's a bit of a blurb about myself. If you have any questions, just send me an email, okay? Connect with me somehow, and answers are free, okay? So certainly want to help people out. So I don't blog a lot, not much happening with Twitter. I keep promising to do that, but it never seems to happen. But as I said, that's the contact details. So if you have any questions, please don't hesitate to ask. Otherwise, welcome to the most exciting session on SQL Server technology since cascading updates and deletes, I think. So what we're going to be talking today is about what they've now called in-memory table, OLTP tables or something. A lot of the stuff that I'll be talking about is based on CTP1. So CTP2 is coming out shortly. Some things are going to change. So some of the answers to questions might actually change. So just be aware of that. So this is all based on CTP1. So just be aware of that. So what I want to do is just introduce the technology, so what Microsoft has been working on. So again, this is something that I became aware of from Microsoft possibly 3-4 years ago, and sort of been playing around with the technology in excess of a year. So it's not something that they baked overnight, dreamt up overnight and baked. This is something that they've been working on in the background secretively, investing a bit of R&D, etc., for the last couple of years. So it's slowly coming to fruition. So it's going to be released in the next version of SQL, which is 2014. What else can I say initially? So again, we're going to talk a little bit about the positioning of the technology. This could be a whole day session. Okay, so what I've tried to do in this particular session is give you a bit of a feel for what this technology does, how it's positioned, what it will do, etc. So we're not doing like a deep dive, although there is deep content into the architecture of how it works. But I think as a DBA after this session, you'll walk away hopefully with a sense of this is the new roles and responsibilities I'll have as a DBA. So there's a new set of concerns and new questions that you need to ask. And you might have to think about Hackathon if you're implementing it in a cluster environment or availability group environment. You need to go and rethink about what you're doing with hardware potentially, etc. Because things work very differently from what you might have been doing for the last decade. So it's that sort of different in terms of a mindset. So just have a little bit of an introduction of what's happening in the industry, what Microsoft is trying to do with the technology, and then we'll go through the internal architecture, have some small demos, okay? And then just talk a little bit about the DBA side of things. I sort of forgot to submit a session for TechEd about the developer side because that would have been a separate session. So maybe next year we'll do another one. If you're in a user group, Sydney or Brisbane, I'll be talking about the developer side of things in the Sydney and eventually at the Brisbane user group at some point in time. Okay, so just be aware of that. So let's get underway. So let's have a look at the introduction. So talk a little bit about industry trends, this Hackathon project, and sort of the design pillars that Microsoft have sort of come up with for this particular product. Let me just ask a very simple question, loaded question, dangerous question. What's wrong with SQL Server? Sorry? Oh, anything else? Sorry. Too expensive. Okay, all right. Okay. One of the things that I think about the SQL Server, it's been around for quite a long time. Okay, so remember, it was developed back, SQL Server days, 6, etc., when we had machines that were single processor, 16 megabytes of memory, not even that much, 12 megabytes of memory possibly, running on a 386 instruction set. And hardware has changed a lot since that time. The problem is that, the SQL Server architecture, the engine has been based on that sort of an architecture of processes. And things have happened a lot since then. Okay, so with multi-cores, large caches, symmetric multiprocessing, etc., we'll be looking at some of this. So Microsoft a couple of years ago said, we're releasing different versions of the product and we're sort of improving performance by, 10%, 5%, etc. But what we need to really sit down and think about is how are we going to improve performance by 100-fold? So take into account modern processors, the size of the level 3 caches, level 2 caches, etc. So this is what they've been thinking about. So let's not give incremental improvements in performance. Let's try to give you an order of magnitude or a couple of orders of magnitude improvement in performance. So this is where column store and things like that come into play. So that's part of that sort of story of trying to have an engine that will take the best advantage of current hardware. And Hackathon's something that fits into that as well. Okay, but we still have that core relational engine with extents, 8K pages, etc., etc., etc. So let's have a look at some industry trends just to sort of set the context. So again, this shouldn't be a surprise, but over here we have a nice little graph which is talking about industry trends with CPU. So you can see again, Moore's law is still very, very true. So we're fitting more resistors, so doubling resistor density every so often over here. But you'll notice that these days the industry has changed. So again, a decade, 2 decades ago, what were we doing? We were making computer chips or CPUs faster. So faster gigahertz, more gigahertz if you like there. And because of a variety of reasons, but these things would melt if they ran at 6 gigahertz, etc. What have we gone and done instead? We're not driving faster frequencies. What we're doing now is going to multi-core processors. We've got Intel's hyper-threading coming to play, etc., etc., etc. So you can see on the graph over here that clock speeds have sort of stalled. You would have expected, if you were talking about this in 2005, that we'd be running processors at 6, 8 gigahertz, but we're not doing that at this particular point in time. We've got octa-core, deca-core, etc. Processors coming out over here. So in terms of performance there, as you can see, the performance per clock cycles or instructions is still sort of logarithmically starting to sort of peter out, if you like there. So we're not driving faster frequencies, we're sort of concentrating on more cores, larger caches, Intel's hyper-threading architecture, etc. The other important industry trend is that memory is continuing to fall in price. Okay, so the sweet spot for RAM these days is 16 gigabytes. I think you could almost say that 32 gigabyte DIMMs sticks, if you like, are much more affordable there now. So they're going to be the sweet spot. And as we know, for SQL Server, your CPUs aren't going to be the bottleneck. All of your SQL servers are most likely I/O bound. So the more memory you have, the more you can cache, the less need there is to go to disk. But as we discussed in our secret talk before this session started, we've got a whole bunch of hardware that can alleviate that problem as well. And again, there's some other features in 2014 with SSD buffer pool extensions that will improve that story there. DDR4 is coming out soon. So again, not quite mainstream. People are predicting 2014, maybe 2015. So again, faster speeds, higher densities, yada, yada, yada. As a little bit of a tangent, something that I'm sort of keeping my eye out on is something called HMC memory, so hybrid memory cubes. So again, I'm not going to talk too much about this because I don't know too much about this, but I'm watching this particular space. So this is interesting because this is like 3D memory. So the bottom line is that you have higher densities of memory and you have memory that works at faster speeds by orders of magnitude. So it's already been ratified as a standard. I think the first versions are out in the second half of this particular year. They might not be high capacity, but you might find that in a couple of years you'll be buying these things to plug into servers that could be, I don't know, 16 gig sticks and then 64 gig sticks and then 128 gig sticks. So it's not inconceivable that in a very short period of time, I'm not making predictions, we're going to see servers that are affordably sitting with 4 terabytes of RAM there that you can use. Okay? So again, something to watch out with, something to think about, something to discuss later on tonight, possibly there. So in that sense, it was sort of the correct timing for Microsoft to get into this space within memory technology. So there are other vendors who have in-memory technology. Again, we discussed that before this particular session, but their approach has been slightly different. Some of these other database vendors have bought a product and sort of it's a different offering from the core product. So Microsoft have taken a different approach to this, as you can see. But the bottom line is, as I said, that this was sort of the right time for Microsoft to get into this in-memory game for database technology. And it's something that they've been working on, as I said, for the last X number of years, 4 years plus. Okay, so again, got access to the technology a couple of years ago, but they've been working on it for quite a while. Now, again, they've come up with an official name, but this was actually internally called the Hackathon project. And as you can see, the word hackathon is derived from the Greek word, who's Greek here? Hekaton? I don't know, so pardon my Greek, which means 100. So the idea, as I said earlier on, was we're trying to improve performance by an order of magnitude. We're not trying to improve performance by 10%, 30%, 100%. We're trying to improve performance by 100-fold. That's what we're trying to do with this technology, which again is substantial. So it means we have to completely rethink the way we're doing things and look at the current problems with the database engine and try to optimize it with the harder. So that was the sort of proof of concept goal for this, and that's why they sort of called it Hackathon. Now, this is not just about putting things into memory, because we could do that. We could take our current B trees, heaps, whatever it is, and put them into memory. But things would not necessarily be faster, okay? Because you've got scans going on, you've got seeks going on, you've got different access methods going on, etc. So it's not just about putting things into memory, because you still need to traverse structures in memory, okay? So we need to rethink things. And you can see over here Microsoft did a bit of analysis, and you can see here on the right-hand side, they've sort of had a look at where we're spending execution time on the servers executing SQL code. So if we put things into memory, you can see over here, the I/O and thread management only represents 10% of the overall computation of something executing. So we're not going to get a big win by just putting things into memory. So again, you can see over here, we've sort of color coded him. In the blue, that's the storage engine. So the access methods over here, locking, managing the transaction log. Think about the transaction log. We write to the transaction log, we have to write the transaction that we want to perform, we have to have undo information, we've got redo information, we need to modify non-clustered indexes, etc., etc. We have to modify GAMs, SGAMs, PFS pages, etc. There's a lot of stuff that happens inside the transaction log. And again, not optimal I/O in that particular case as well. So the idea here is we need to do more than just put things into memory. So we need to hopefully execute things faster by improving the storage engine, but also the relational engine as well, the green section. So again, think about how SQL code gets executed. We've got to parse it, normalize it, generates an execution plan, parallelism comes into play. There's a lot of processing that goes on in that particular case. So again, you can see from their sort of baselining, 35% of the execution time spent in their space. So it's not just about, putting things into memory. There's more that needs to be done if you want to optimize performance. So there's two components, basic components, if you like, inside this new engine, this Hackathon engine as I'll call it. So the idea here is we not only want to put things into memory and have new structures that are efficient for memory-only usage, what we would also like to do is improve the execution of the SQL code as well. So not this interpreted stuff that's going on. So we now have a compiler as well. So there's two components of this new technology that's coming out in the next version of SQL. So let's have a look at the design pillars, if you like. So what Microsoft have tried to achieve with this product and the drivers for that. So again, first thing we're talking about is high performance data operations. So again, it's not just about putting your B tree structures into memory. What we want to do is design a new engine, if you like, there that's optimized for memory. We don't have to worry about disk considerations. We don't have to worry about lazy writers and all this sort of stuff. So we'll cover this in more detail, but we've basically developed an engine which has a new row format for the data, and it's optimized for traversing things inside memory. So forget about all these non-clustered indexes, clustered indexes, heaps, etc. There are no more pages that have this redundant information. So it's completely different, okay? We have different indexing technology. So we have hash and range indexes, and they exist only in memory. We don't use the buffer pool at all. Okay, we don't use the buffer pool at all. We have other RAM that is dedicated to the Hackathon engine. Again, we'll talk about this. So again, the drivers, as you can see, memory is becoming cheap, faster, etc. So take advantage of this potential plethora of memory that we have. The other side is, the next thing that we're talking about, is the SQL execution, if you like, there. So again, when we're traditionally executing transact SQL code and having all these execution plans, taking up the procedure cache, etc., again, it's not particularly efficient on modern hardware. So what we've done in this particular case is compiled your SQL code to machine code. So when you create a stored procedure that's native to Hackathon, you're actually creating DLLs that are sitting on the engine. You actually do it for the tables as well. So the idea here is these DLLs become an entry point for reading data from memory and also executing stored procedures. So completely different. We might have to hold off on questions. I should have mentioned that because I'm probably going to answer most questions and we have a lot to go through. So sorry, Justin, okay? So again, we don't have to worry about reusing execution plans. As you can see, we've got aggressive compilation. So again, we're going to improve performance over here. So again, the driver for this was we're getting more cores, but we're not driving faster frequencies. So this is the way we can potentially solve this particular problem of poor execution. The other thing that we have, again, in terms of performance, people are always worried about hardware, bad execution plans, whatever. But the problem is that fundamentally you also have concurrency at play. So whenever performance is bad, one of the fundamental reasons might be is because you've got multiple people inside the system. So if you have multiple people inside a system potentially trying to modify the same data, what do we need to do? We need to lock the data. We need to isolate transactions from each other in that particular case there. So again, we've got concurrency control, we've got locking, we've got latches. So if you do away with that, you don't have any of that particular problem. So again, by the time we finish this presentation, you'll see that with Hackathon, we use optimistic concurrency. So there's no locking, there's no latching going on. Okay, so you're not going to see a performance bottleneck because of that. And again, drivers, multi-core processors. And the final thing again, which is interesting, Microsoft wanted, because of you, to have a similar experience. They could have developed another database engine, and that would have been another technology that you had to learn, manage, install, configure, etc. What did they want to do instead? Let's put this into SQL Server. So you don't have to buy an additional product, you don't have to buy an add-on, you buy SQL Server, you're comfortable with SQL Server, you have a skill set in SQL Server, and you can leverage that. So we've put this in-memory database engine into the SQL Server engine. Okay, like we did with column store. So you've got your buffer pool, you've got your column store data, and now you have your Hackathon data. So again, that memory space for SQL Server is becoming a little bit of a crowded resource. But again, hopefully this is ringing various interesting alarm bells and how we're going to do this in the future, etc. But again, the idea here is minimal work potentially to migrate existing applications to use this particular technology, and there'll be some tooling around that, which I'm not demonstrating, but it's already out in CTPs for you to have a look at. So it's integrated with your high availability. It's integrated with your backup restore, so maybe a little bit of change required, but trying to make it easier for you, okay? So I don't have any Hackathon demos in the sense of, oh, here's a benchmark and the improvements in performance. Microsoft have done a couple of those. So I've just taken a screen capture of some results. So this particular screen capture is where they've got a test harness. It's not a massive server, okay? It's only got 16 cores, 256 gigabytes of RAM, 2 SSDs, 80 users. So again, that's the test harness if you like. And then again, they did some OLTP transactions, and you can see the baseline of 2,400 transactions per second. And then what they did was they put the tables into memory. Okay, so the tables that were on disk tables, now reside in memory. And by doing that, they got 17,000 transactions per second. So that's a 7-fold improvement in performance. And again, we're not talking about 30% more, 100% more, we're talking about 700%. Then what they did in the second phase is take the stored procedures and compile them natively into the Hackathon procs, if you like, there. So now you can see we've improved performance by 27-fold, so almost 30%. So obviously your mileage will vary, but from all indications with Microsoft testing so far, sort of the vision was 100-fold, but you're getting up to 30-fold improvement in performance. And obviously it depends on the context of your environment, etc. So already they've got customers that have been involved in TAP programs who have been using this. You might have heard of some, BWin in Europe, that are doing things like that. So again, minimal work hopefully, and again, you can realize some really good benefits out of this technology. So here's another example of the scalability. So again, I'm not going to go through this. You can look at the PowerPoint slides later on, but you can see they've got a graph there with the number of cores, and then, you know, the transactions per second based on the cores, one SQL with contention, without contention, native procs, and those sorts of things here. But this is the interesting thing that we now have the capability of taking advantage of. So again, can completely rebuild applications to take advantage of this and possibly get massive improvements in performance there. So let's have a little bit of a look at the architecture of Hackathon. So I want to have a look at Hackathon from a high level and then talk a little bit about the transaction log, because that's one of the wins that they've gotten with the Hackathon engine, if you like, there. So this is my little diagram of the Hackathon architecture at a 1,000-foot view. So this is what you have existing inside SQL Server right now. Okay, so from the key on the right-hand side, you can see the grey bits of SQL Server. Down the bottom, you can see we've got a transaction log and a database file. So we've got the usual bits and pieces. I'm not going to go through them. You can see over here, the important thing is that we have the buffer pool, and we're buffering both the tables and the indexes. And again, as you're modifying database tables and modifying indexes, again, you're storing the data and the indexes in the file group. As you're modifying all of this through your DML operations, you're obviously also writing things to the transaction log. So the transaction log does tend to be quite verbose. So it's not just inserts, updates, and deletes. It's all sorts of internal stuff that also needs to happen to the indexes and so forth there. So the first thing that we talked about is that we have the capability of putting tables from disk-based tables to memory-only tables. So in this particular example, you can, oops, went the wrong way. We're going to move tables 1 and 2 into memory optimized space there. Okay, so we're going to do that. And one of the things that you'll notice there, hopefully, is that we no longer keep the indexes inside the transaction log. There's no need, okay? So indexes are memory-only structures. We don't need to do anything with them inside the transaction log. So again, that's a saving in space, so it's not as verbose as it used to be. You'll also notice, and we'll talk a little bit about this in more detail later on, that this is memory-only technology, but we still need to have durable tables. So if the system crashes, we need to have the capability of restoring the tables into memory. So we no longer store the tables, if you like, inside the extends, pages, those sorts of things that we've been used to. We've basically got a new storage container which is used to store the memory optimized information, table information, and it's optimized for performance. So let's reinvent the wheel. Sequential I/O only, not random I/O. So completely different. So optimized for performance, and we'll discuss this in more detail later on. But again, when you create a Hackathon database, you're going to have a separate file group. So that's implemented on the file stream. We still have the checkpoint recovery, okay? So if things crash, things go wrong, you know, we don't lose data in this particular case. We also have the capability through the query interop to access the memory-only tables via your traditional T-SQL. So you won't get the full benefits of Hackathon in that particular case, but you'll get that 7-fold improvement in performance, possibly. Otherwise, we now have this compiler inside the SQL Server engine as well. So as I said, when we create a table inside Hackathon, it actually creates a DLL for that table, okay? Because we don't use the access method managers anymore. So the DLL becomes an entry point into accessing that particular table in memory. So the tables are effectively DLLs, and the stored procedures are DLLs as well that get called, okay? Okay, and the last thing over here is that we now love this particular feature. I could have used it with a number of customer sites. We also have the capability of saying tables are not durable. So they're memory-only tables, and if the server crashes, we reboot the server, restart the server failover, the data's lost. And there might be a variety of reasons for that. Okay, I don't know if people can come up with a use case. Session state information for a website. If that server crashes, what's the point of storing all of that session state information? Your sessions have disconnected, etc. So they've given you that capability as well of saying that tables are no longer durable. So you can see in this particular case, they're no longer in that particular memory optimized file group as well. So let's now have a look at the data structure. So again, things have changed. So as I said, we need a degree of backward compatibility with the SQL stuff that we're used to, but we have a completely new row format which is optimized for in-memory access, okay? So we have a completely new row structure, as I said, optimized for memory access. There's only one copy of the row, so it's not right now the situation where we have a clustered index, a non-clustered index, multiple non-clustered indexes, included columns, so my surname is located in 5 different B trees or whatever the case is. There's no need for that. So the idea is we're much more efficient with what we're doing in memory, and if we are optimizing it for memory access, we don't need any of this information. We're talking about memory only here. So again, indexes point to rows, they don't duplicate them in that particular case there. So with CTP1, all they have implemented is hash indexes. In subsequent version, and by the time the product RTMs, we're going to have range and indexes. So we're going to have more indexing structures to support different types of searches there. Notice again, as I said earlier on, the indexes don't exist on disk, okay? So they're created in memory only. So you've got indexes and data, Hackathon data, but you can create, I think, up to 8 indexes from memory. But the idea here is we don't have anything happening at the disk drive level. We're not storing anything for durability purposes to reconstruct the indexes, etc. Okay, you'll see why in a short while. So this is just a graphical representation of the row format. So again, I'm not going to spend too much time here, but it's quite simple. So you've got a row header, and then you've got the payload, the actual data, if you like, there. And the row header, as you can see, is quite simple. You've got the begin timestamp, you've got the end timestamp. So that's the temporal information for when this particular row is valid. Because what we're doing, as I might have mentioned, I hope, is that we're using optimistic locking. We don't have any locking going on, so we have optimistic locking effectively in the product there. So we have row versioning, if you like, there. So you have this begin and end timestamp, which is the temporal data for what transaction can read this particular piece of payload, if you like, there. Then we have a statement ID, so what modified it, and some stuff there for the index as well, some pointer stuff over here. Okay, so again, the begin end timestamp is important. There's no data or index pages because we just have this one format for data. The row size is limited to 8,060 bytes. Why? Quite simply because we want to move SQL tables into Hackathon and Hackathon into SQL tables. Okay, so a bit of an artificial construct, if you like, there. So what about things like varchar maxes, text, image, data types, etc.? They're not supported. Okay, so not every data type is supported inside Hackathon. Okay, so again, we're not doing the developer session, but there are some restrictions. Identity isn't supported, sequence isn't supported, but there are ways around that, etc., etc. So this is what happens when you update a row in Hackathon. Okay, so we've got a couple of indexes, somebody living over here, pointers, etc. But this is fundamentally what happens. So we're sort of really paying attention to the timestamps. So the timestamp for this particular record is it was inserted at 100, and the end timestamp is effectively a special marker. I don't know what it is, but it represents infinity. Why is it infinity? It's still valid because it hasn't been deleted or updated effectively. Okay, so the idea here is that if somebody modifies a row in Hackathon, as you can see, we allocate a new record. So this is transaction number 2 firing off. So we've got a new instance of it, if you like, there. Then what we need to do is start to muck around with the timestamp. So this transaction's timestamp goes into the end record and the begin record effectively. We manipulate some pointers because we need to traverse this to find the record, if you like, when we're doing the optimistic concurrency. So we need to update some links to the indexes. And finally, what we're going to do is commit the transaction. And that happened at timestamp 200. So you can see for the old record, it was valid from 100 to 200. The new record now is from 200 to infinity. So we don't actually update in place. Okay, with Hackathon, we only do inserts and deletes to the data, as you can see. Okay, so over here we have a deletion of a record. Oh, what's happened here? Oh, yeah, that's fine. Sorry. Okay. So this is deleting a record. So again, we've got a record that's going to be deleted after the previous one. So again, here's the current state of affairs there. So we're going to have to do something very similar. So as you can see, we start to go through this particular transaction. So there's TX3 being written to the header. We commit the transaction, timestamp 300, so we commit to the delete operation. So basically now this row is invalid. It's not deleted, as you can see. Okay, so it's still sort of in memory, if you like, there. So obviously after a period of time, we're going to get something like this. So we've got all of these different versions of records inside memory. And that obviously has a number of problems. Okay? If we want to traverse these structures, it's going to take longer because we have to jump through all of these links to get to the version of the record that we're interested in, if you like, there. And obviously we're also wasting space because again, we don't modify data in place. We'd need locking for that. Okay? We don't delete immediately. Again, that would require locking. So we're avoiding locks altogether. So we have this row versioning happening automatically in the background. Obviously, we need to reclaim this wasted memory because right now we're at transaction maybe 300 or something like that. So there's no point in keeping transactions that have finished at 100 or 200 because nobody can access them. All the transactions have completed by then. So we obviously need something that reclaims the space, some sort of garbage collection, if you like, here. So again, a little bit of information about the garbage collection. So again, updates, deletes, aborted insert operations, create row versions. Eventually we need to clean them out because it's taking up memory, slowing things down, etc. So we need some sort of garbage collection. So we'll have a little bit of a diagram of that coming up shortly. But effectively the system keeps track of the oldest active transaction. So that means that we know what we can get rid of because there's no transaction that's currently accessed can potentially access the data in those particular timestamps. So the design goal is obviously high performance. Okay, so again, you get a sense of sequential I/O, no locking going on, etc. So we've got a dedicated thread that's going to do the garbage collection, but at the same time, we've got a multi-threaded environment. So why not take advantage of other threads that can potentially do the garbage collecting collection for us. So we've got a dedicated system thread to garbage collection, but you can see that other transactions that might be scanning the data could potentially also help with the garbage collection. So again, non-blocking, cooperative, efficient, trying to get the best performance. I've never had so many photos taken of me. I should have cut my hair and put on some makeup. So here's something about the cooperative garbage collection. So the idea here is we've got a dedicated thread, but that could potentially become a bottleneck. So the idea here is now we have the capability of, as threads or processes are accessing the data, scanning this particular linkage to get to the data that they're interested in, they can also at the same time get rid of old versions of records effectively there. So you can see we've got transaction number 4 here, began at 210. The oldest active transaction is 200. So the idea here is we can get rid of some of this as we're going through this set of pointers, if you like. So again, just a little bit of an animation. After the cooperative garbage collection, we're going to see these particular rows disappearing. So dedicated system thread, but also why not help out while we can. So let's talk a little bit about memory management. So this is memory-only technology, which means what? The disks aren't involved really, for all intents and purposes. So it's not as if we run out of memory inside the hackathon's memory, if you like, there, that we're going to start paging to SQL or things like that, okay? So if you run out of memory, you're going to run out of memory. So as a DBA, you're starting to hopefully think that we have to manage this very much like storage. So we know that we're going to run out of storage next week, so we need to order some more LUNs for the SAN or something like that. If we run out of space in the transaction log because it fills up the disks, we're in trouble, etc. Now you have to start to think about this for Hackathon as well, because you're saying this data only lives in memory. So it's not going to live anywhere else. So again, big recommendation, DBA, walk around with a 64 gig DIMM or a set of them. So if you start to run out of memory, put them into the server, because it's going to be like that almost. Okay, so capacity planning goes a long way in this particular case. So the Hackathon data resides in memory all the time. There's no paging going on, if you like, there. So the maximum supported 512 gigabytes. I don't think these numbers are going to change there. If you want to insert data, update data, delete data that's inside Hackathon, and there's not enough memory, transactions are not going to complete. You're going to start to see errors, okay? So again, integrated with the SQL Server Memory Manager, so it'll react to memory pressure as required, but there are some hard limits. So again, you can see 80% of the physical memory is a hard limit. We've got the 512 gigabytes as a hard limit. They don't have integration in CTP1, but in CTP2, they'll have integration with the resource governor. So you can sort of control it at the database level as well. So not in the current CTP, but it will be out in the next CTP, which is going to be released anytime between now and the future. So in terms of memory guidance, this is what Microsoft is saying, capacity planning. Again, your mileage might vary because you know that inside your environment, people are only ever inserting transactions, then ever deleting and updating. So again, this is sort of generic guidance. It's quite generous, but you might change the recommendation for your particular environment. So you can see for the table data, Microsoft is recommending 2 times the actual data that you think is going to be there. And that's because of the deletes and the updates taking up extra versions as well there. For the index data, again, it's a hash index, so it's simple. It's the bucket count times the pointer size. Okay, quite simple. And again, from a management point of view, you're going to have resource governor as discussed, and you're also going to have some DMVs, SSMS tools, and things like that as well. So memory troubleshooting, I really like this diagram because the funny thing is it all sort of starts off differently here on the left-hand side, but it all ends up at the same place. Okay, so you can see over here, you're trying to insert more records, can't fit into memory, those transactions are going to start failing. What are you going to see? Well, error log messages, DMVs reporting this information, resolution. As I said, it's like a disk resource. You need to free up memory, you need to add up additional memory, or kill transactions that are running. Okay, next one. Your system reboots for whatever reason, database needs to load into memory, nobody can access it before that happens, there's not enough memory because there's now an extra instance of SQL installed on that cluster node. Might be a variety of reasons. So again, the database won't come online until you solve this particular problem. So again, same sort of path in terms of troubleshooting. And of course, the other thing that can happen is that Hackathon can consume a lot of memory, so that starts to put pressure on your non-Hackathon workload. So again, the non-Hackathon transactions might start failing. Again, same sort of resolution fundamentally. So let's talk a little bit about transaction logging. So we sort of integrate with the existing database's transaction log, but we also have our own little file group which takes care of the durability aspect of things there. So the idea here is we need to sort of intermingle the hackathon and the non-hackathon transactions. So that's why we use the database's transaction log, but we're much more efficient. Because as I said, we don't need to have any redo information and things like that. We don't need to have any index manipulation, etc. So the hackathon records inside the database's transaction log are going to be much more efficient, much leaner. We don't write as much information because there's no need to write that information there. So each hackathon log record, and we'll have a look at this in a short while, will basically be, this is a hackathon record inside the transaction log, and then it'll be the payload, what happened inside that hackathon transaction. So we'll have a demo of that in a short while. Down the bottom, as I said, very, very important, we're much more efficient with the transaction logging inside the database's transaction log there. So we don't worry about all this index manipulation, GAMs, SGAMs, PFS pages, etc., etc., etc. There's no need because we're using a different row format. It's a memory-only construct. We don't have to keep track of the indexes because the indexes get rebuilt in memory if something goes wrong and we need to restart the server, etc. there. So you can see redo only log records in the transaction log, so much, much more efficient. So that brings us to the first demo. So let's have a little bit of a play around with this. Everybody cross your fingers. Okay. So what we're going to do is create a database. Ooh. Very, very sensitive. Okay. So what we're going to do, I'll just refresh over here to make sure. So we're going to create a hackathon database, and you can see the semantics are slightly different. So again, we've got the transaction log and we've got the data file, but you can see now we create a file group, and that's for the memory optimized data. Okay, so this is where effectively the durability of the hackathon tables is going to reside. We're going to talk about this in a short while there. So I'm just going to run that, and I'm going to set the database to simple recovery model. So taking a little bit of a while because it has to start up or write the hackathon file group stuff in there, pre-populate some tables. So I'm just going to switch across to the database. And what I'm going to do is create a hackathon table. And again, you can see the syntax is slightly different. So the main thing that hopefully sticks out is that we've got, as you can see, a couple of things there. Memory optimized is equal to on, so this is telling it's a hackathon table. We're interested in durability of both the schema and the data because, as I said, you can have tables that are not durable. So the schema will exist, but if we reboot the server, the data will be lost. Okay, so we have the option of doing that. And the other thing you can see, we're using hash indexes, so we need to put in a bucket count as well. So Microsoft will have some guidance on that. We can talk about it later on. But as I said, you have now some serious capacity planning like you did when you had SQL Server 6 and were trying to run it on a 12 meg machine, 386. So just execute that particular table. So again, it's creating some DLLs in the background to represent that particular table. So what I'm also going to do is create an equivalent table for the traditional disk table. So call it disk table, so pretty much the same thing. And let's put some data into it. So I'm going to begin a transaction and just insert, what is that, 1,000 odd values. Okay, so that's going to be into our disk table. Okay, so it didn't take long. And what I'm going to do is have a look at the transaction log. So just access the function db log, no timestamp, and tell it to look at that particular object, disk table. So again, I'm not too interested, in what's in the transaction log. I'm sort of interested in the number of records and also the log record length. Okay, so these are the sorts of things to look at. So again, let's have a look at how many records. So we inserted how many records? 1,000 records. But as you can see, as far as logging is concerned, there's about double that volume. Okay, so we've got a bit more to do in that particular case than the actual number of records. So again, sort of have a look at that. We're modifying the heap and the non-clustered index there. Okay, so again, that sort of physical logging has to occur there. Let's now do the same thing for the hackathon table. So begin a transaction, insert 1,000 records into the hackathon table. Okay. And just look at the transaction log directly. Okay, so I'm not going to put any filters. So if we scroll to the very, very end, we can see over here a slightly different story. So there's the begin transaction, there's the end transaction, and there's the hackathon records over here being inserted. So try to highlight those. So again, less activity, but you'll notice over here the log record length is larger. So you can see over here, instead of whatever it was, 1,000 bytes, etc., it's now 23,500 and so forth there. So completely different, much more efficient logging. So that's part of the win that you get. So let's have a look at that in a little bit more detail. So what I'm going to do is checkpoint the database for no particular reason, but what I want to do is flush the transaction log because we're in simple recovery model, we're in that auto truncate mode. So what I'm now going to do is update that disk table and just, update it. Okay, so that's the disk table. Okay, 1,000 rows modified. And again, if I have a look at the transaction log, we're going to again see in this particular case, 4,000 rows inside the transaction log. Okay, so again, you can see over here, doing some information, what's going on here. So what I'm now going to do is just, are we up to here? So checkpoint the database and compare it to the Hackathon environment. So again, let's update the data. 1,000 rows have been modified. Okay, and now what I'm going to do is have a look at the transaction log. So again, we had 4,000 odd last time. You can see in this particular case, we've got a lot less activity in this particular instance. Okay, so again, sort of go towards the end. And I need to look up something, so let me just quickly, let me have a look at this. Let me just run that process. Let me have a look, sorry. So where's our, okay, so I think I want to concentrate on that particular log record. So what I can do, getting slightly different output this time, is crack open that Hackathon log record, is what I'm trying to achieve here. So if I execute this, notice we're going to a different function. Oh, no, that was the wrong thing. This is why I don't like doing demos. Okay, let me just do this again. This will be the easiest way. Oh, so we've updated the record. Have a look at the log. Ah, here we go. That's looking a lot better. So we put that value in. So you can see the payload's that 23,500 length. So what I can actually do is crack that open. Okay, so if I crack that open, you can see these are all the Hackathon update rows for that particular transaction. Okay, so again, just trying to highlight the fact that we're getting wins here already because we're using a different architecture internally inside the transaction log with how we're working with the Hackathon data. So let's have a look at another aspect. So we sort of said there's no locking going on. So let's have a look at that side of the Hackathon engine there. So what I want to do in this particular case is just put some more data into the tables. So begin a transaction and insert, what is that, roughly 1 million records into both the disk table and the Hackathon table. Okay. So we saw inside the earlier diagrams that, again, we're not sort of updating things in place. We're not doing direct deletes. What we're doing is creating all these different row versions, if you like, there that represent a record being updated or a record being deleted. So this is going to take about 30 seconds to complete. Okay, so Victor's got to start up Perfmon. Okay. So Performance Monitor. So with Performance Monitor, apologies, that might be a little bit hard to read. Just very, very simple example. So what I'm doing at the moment is monitoring the processor time, and then what I'm going to do also is monitor the total lock requests per second, and I'm also going to monitor the page lock requests per second and the row ID lock requests per second. So, start it up. So we're going to start that up. Okay, so it's running. So as you'd expect, probably using a bit of CPU. But there's no real locking going on at this particular point in time. So I've highlighted or made bold the total lock requests per second. So what I'm going to do is just update the disk table. Okay, so I'm going to update the entire table. Okay, so that's going to take a little, well, it's not going to take too long to complete. And I'm just going to pause a little bit so that we can see it inside the graph. And then what I'm going to do is update every 5th row inside the same table. Okay, so 20,000 rows modified as opposed to 1 million. So if we go back to performance monitor, you can see we have had some lock requests. So we've got locking going on here. So that's the total number. And you can see if I go down to the page lock requests per second, that both the first and the second transaction had page locking going on. But if I go to the row locking requests, you can see that when we updated the entire table, there was no need for row locking. We just used page level locking. But you can see over here that for the second transaction, we needed row level locking there. Okay, so we used row level locking in that particular case there. So of course, that's a combination of intent exclusive plus exclusive locks in the background. So let's do the same thing with Hackathon and see what it does. So again, update the Hackathon tables, same operation. So 1 million rows have been affected. Wait 5 seconds and a bit more, and then update E. Every 5th row. And quickly go to perfmon and pause. And you can see that in this particular case, if we go to total lock requests, well, I expected a slightly different graph, okay? But you can see that although we haven't had peaks in this particular case, we have had some locking. So that's the total lock requests. I thought you said, Victor, you're lying to me. There's no locking going on. But let's verify that. Let's have a look at the type of lock. So if we go to page locks, you can see there's been no page locking, okay? And you can see that if we go to row locks, again, there's been no row locking. So what's going on in that particular case? Well, let's see if we can answer that question. So what I'm going to do is turn on a couple of trace flags. So this one's not documented. I'm a big fan of it. Please, please do not run this on production environments. Please, please do not. Okay? Unless you're a consultant. You put it on this trace flag, they're going to complain about performance diving atrociously, and then you can come in and solve the problem and charge a fortune. Okay? But seriously, this will harm your systems. But it's a good tool for developers. It's a good tool for understanding the engine. So what I'm talking about in particular is trace flag 1200, which is going to give us locking information. So I'm just going to turn on a couple of trace flags. So 1200 is the undocumented one, the secret source. That's going to give us locking information in real time. 3604 is just telling us to write the output of 1200 to the console, to the management studio. So what I'm going to do in this particular case, possibly switch to, no, I can, no, yeah, okay, I can do it this way. So I'm going to put the results to text. And what I'm going to do is update the Hackathon table, exactly the same operation as before. Now, the difference in this particular case is that you're going to see in real time the locking that is going on as you're performing this particular operation. So again, we don't really have any row level locking, page level locking of the actual data. What you're seeing in this particular case is sort of the schema stability locks, the database locks that are preventing people from dropping the tables and those sorts of things. So again, the idea here is that there's no locking of the data going on in this particular case. There's just a bit of locking going on there for protection of the schema of the environment itself there. Okay, so let me just turn that off. Oops. And go back to the slide. So let's talk a little bit about durability. You saw in the high-level overview of Hackathon that we have this concept of a file rope that we use for the durability aspect. Okay, so it's a memory-only table, but it needs to potentially survive a server being rebooted. Okay, quite simple. There's important data in there. So the transaction log gets backed up and wiped. So we're not using the transaction log for the durability aspect of that. So inside that file group container that we've got from the Hackathon database, we have the capability of saying that this particular table is durable. So you saw that when I created the table. Durability was table and schema. So what that means in this particular case is that Hackathon is also going to write, checkpoint effectively, information to a set of files that will enable it when the server restarts to rebuild the in-memory tables there. Okay, so the implementation is file stream. Okay, so that's why I needed to create that file stream container. And again, to optimize performance, can have multiple containers, etc. Okay, so again, we'll talk about this in more detail later on, but as I said, I think earlier on, in-memory database tables, in-memory data needs to live where? in memory. There's no trick questions here, okay? So the idea here is when we reboot the server, we have to load all of that data into memory before we allow access to that database. So if you have 10 gigs of data in a memory-only table, guess what? You need to load that 10 gigs into the table, which implies what? Time, absolutely. And time can be reduced by your I/O subsystem, okay? So if you've put that onto a USB drive, it's going to take a long time to restart that database. So again, DBA, architect, whatever, should be starting to think, we're going to maybe design things differently. So if we have SLAs around cluster, database availability groups, etc., 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 things need to come up quickly, what do we need to do? We need to maybe think about SSDs for the Hackathon containers, the file streams, because it's going to improve recoverability for larger systems. Okay, so one of the key points. So have to start thinking about hardware a little bit. Okay, so this is basically what happens. So we're going to see a diagram of the data and delta files in a short while, but this is a sort of a high-level overview of what's going on. So we write our operations to the transaction log, but we also, for durable tables, have this file group which is going to keep track of a data file and a delta file, which we'll explain. But this is the nice animation that I've been working on for a week. So I learned so much about PowerPoint animation, and you'll see my arrows aren't very good. So here comes the delete operation. It's timestamp 150. So over here you can see, and we'll explain this in a short while, we basically have all of the inserts inside these green files, and the red files keep track of the deltas, the changes. Okay, so we'll explain this in a short while, but fundamentally this is what's happening. So we have a delete operation, it's modifying something at timestamp 150. So when Hackathon does its checkpoint, basically what it's going to write is a piece of information to the delta file for that timestamp. So at 150, a record was modified. Then over here, we have another operation coming in, which is a delete 250. So again, we're going to write that to that red file. And again, you'll notice after the arrow disappears, the delta file increases. Okay? And then again, we might have an update. So an update is really what? An insert and a delete combination. So we delete the old version and insert the new version of the record. So this over here represents the old, this over here represents the new. Okay? So this is basically what's happening in the background. And then we might have an insert. So an insert basically goes into the last one. So the idea here is we have these data and delta files there. So each data file is approximately about 128 megabytes in size. And after it gets to that size, we sort of cut it off. So again, we're trying to optimize performance. Okay? So it's only sequential I/O because we only have a write to it. Okay? So the idea here is we're going to use this information to load the database into memory there. So again, at 128 megabytes or thereabouts, we cut things off, and then any row modification, in other words, a delete, is happening via this delta file there. Okay? So all I/O is sequential, trying to take advantage of the hardware in the best possible way. So again, this is the Hackathon storage for the durability aspect there. So again, some of this is repetition. 128 megabytes size in files, stores only the inserted data. There's no indexing information because the indexes get rebuilt when we load it into memory, okay? Everything's sequential, so chronologically ordered streams of new row versions. The delta file itself is much smaller because it basically just contains the deleted records IDs. As you'll see in a short while, we've got the format file coming up. So this is the Hackathon storage. For its durability, data and delta files, and we saw previous examples of the transaction log. This is what the data delta file looks like. Quite simple. For the data file, which grows up to 128 megabytes in size, this represents 0 through to 100 timestamp. You're going to see the timestamp for the insert, the table, the row, and then the payload. For the delta file, very, very small, because all it is the insert delete combination and the row ID in this particular case there. Okay? So, what happens when we need to restart SQL Server? So, we'll cover that actually in a short while. This is talking a little bit about the checkpoint. Okay, so we're modifying things in databases. Okay, we have our SQL Server checkpoint. Top half of the screen is talking about the SQL Server checkpoint. So it runs every so often, and that can smack our subsystem, disk subsystem. Okay, whereas the Hackathon checkpoint's not really tied to the SQL checkpoint. It operates in the background, okay? You can trigger things, you can see some thresholds over here. This might change in subsequent versions of the product. But the idea here is that this particular checkpoint's sort of running all the time. And as you're modifying data in the hackathon tables, it's writing the information to the data files and the delta files, and then closing off the data files as you get to 128 megabytes or thereabouts. Okay, so completely different checkpoint process going on. Okay, so obviously after a period of time, what can happen? You can have a data file, and if you've modified most of the records in that time range, what will happen? The delta file is basically saying 90% of that data file has been deleted. Okay, so we need to do a bit of cleanup. So there's actually a merge operation that also happens in the background, and you can obviously trigger this as well there. Okay, so you can see down the bottom there talking about that. But the idea here is that you'll have this merge operation that merges two or more adjacent data delta file combinations into one. Okay, so again, that's going to improve storage. It's going to also improve recoverability. So this is an animation of that. So you can see over here, there's two data files, 200 through to 299 and 300 through to 399, where a lot of data has been effectively deleted for that versioned information. So we need to perform a merge. So in this particular case, we're going to do a merge of 200 through to 399. So basically, this is what's going to happen. So what we're going to do is effectively combine those two particular sets of data delta files. So as you can see, that gets wiped out, and we have one file, whereas we had two before. And you'll notice now the delta file is basically empty because there's no deletes happen during that time frame. So let's talk a little bit about database backups. So with database backups, integrated with the SQL Server engine. So again, very important for them to have a similar experience. It's just going to work, okay? So it's going to work with your backups mostly. You can see the points here. Backup compression works. Integrated with third-party tools, so possibly no change, possibly minimal change as far as backup strategies are concerned. Certain things aren't supported in V1, so differential backup isn't supported, and again, anything in italics might change. So it's under consideration, but at this particular point in time, certainly with CTP1, there's no checksum validation of the hackathon storage. Transaction log backups, again, very, very similar story. So integrated with a database. So again, you've got hackathon information being written to the transaction log, and then you've got the durability side of things as well. And you can see that there's a relationship between them. So the log backup includes the records and the hackathon storage, so double copy. And again, if something's missing because of disk media failure, corrupting, etc., you might have a problem. Okay, so we're going to have to mitigate against that there. All three recovery models are supported. Okay, so again, nothing to change in that particular case there. And again, possibly some implications if you're doing bulk inserts. So let's have a look at what happens, try to start to tie all of this together. So what's happening on a SQL Server restart? So again, as I said, we need to load all of the hackathon data into the hackathon tables effectively. So down the bottom, as you can see, we've got the data and delta file pairs. So when SQL Server starts up, we're going to go through that normal phase of automatic recovery of analysis, redo, undo phases there. But what's happening with the hackathon side of things is that we load the hackathon information. So we need to load the delta map, because what does the delta represent? The records that have been deleted, okay? And then fundamentally what we do is we pipe all of the data files through the hackathon engine, multi-cored, multi-threaded if you like, sorry. And again, we're loading the data files, and the delta file tells us whether it should be loaded into memory or not. Okay, so that's basically how we're loading everything into memory. Okay, and again, the idea here is it's been designed for multi-core environments. So again, that's why they sort of probably did some testing and said 128 megabytes, cut it off, 128 megabytes, cut it off, etc. So then if you have a machine with 64 cores, we can do all of this in parallel effectively. Okay, so there's no conflict going on, because if a record's been deleted, etc., it'll be fine. Okay, so then we go and SQL Server goes off and does the redo and the undo phase in that particular case. Okay, so the impact on your recovery time objective is going to be how quickly you can load these data files, process them into the hackathon space, if you like, there. Okay, so the size of the tables and your disk I/O subsystem. So let's talk a little bit about failover clustering. So we're close to finishing. So in this particular case, we've got an example. We've got a hackathon database. So you can see tables 2 and 3 in memory tables. Table 3 is not. In this case, something fails, so we have a crash. Okay, so what's going to happen in this particular case? Well, SQL Server starts up on the second node. Okay, we go through this automatic recovery phase. So we load table 3, we load table 2, might take a bit longer because it's bigger. So that's the hackathon data loaded, and now we will allow access to that particular database, so the database is available. So again, size of the tables in your Disco subsystem for the hackathon file stream is going to play a big part in that. What's happening with availability groups? Probably no surprise. So with availability groups, you can see in this particular case, we've got a primary replica on the left-hand side, secondary replica on this side. And in this case, it's a little bit different because, again, as you know, SQL Server is running on both machines. So as we are sending the transaction log buffers, as we harden and send them across the network, what we're effectively doing is duplicating the hackathon side of things there as well. So the hackathon data is going to be in server 1's memory, but it's also going to be in server 2's memory as well. So in the case of a failover, all things being equal, it should be quicker. So this particular server 1 crashes. This particular one has to possibly drain a few things through the queue, catch up, but the database will be available much quicker. Then obviously the server 1 gets restarted, SQL Server loads, the hackathon table is reloaded, and then we sort of start syncing back the other way. So we sort of fully support the availability group technology. I sort of said sort of because there's a discussion as to whether the hackathon data on the readable secondary will be able to be readable. So the non-hackathon data will definitely be readable, but possibly not the hackathon data. So it is there, but you can't access it. Okay, so we're not sure what they're going to do. So as you can see, only SQL Server disk tables are supported on readable secondaries under consideration. Don't know whether it's going to make it by RTM, CTP2, CTP3, CTP20, SQL 2020, I don't know. Okay, so I can't answer that one. So again, completely different story, but a similar story as far as availability groups is concerned. So the final demo is just to show off the Delta files, some reports and auto recovery. So Delta files, very, very simple, nothing really to show off. This is just me going to the file group where the hackathon durability information is contained, just to show you that I'm not making this up. So if you look at this, you can see there's all these files, generally around 128 megabytes in size, some are a little bit larger. All the Delta files are small because I haven't demonstrated any updates, any deletes. It's just been predominant. Oh, I have actually. Ignore what I just said. Okay. Yeah, that might be another database actually. I've got a couple here. What else am I showing you? We're showing you some reports. So let's have a look at the database, a couple of databases here. So I've got a hackathon database that is on a disk drive, and I've got a hackathon database that is on an SSD. So if I go to my disk drive one and go to reports, you'll notice there's a few new things. So we've got, what am I doing? No, don't take it offline. This is why I don't do demos. I've never done this. Bring online. Oh. It's all going. All right, so let's have a look at the SSD one anyway. So let's go to reports. So again, you've got your standard reports, but you notice there's a few differences. So what was I trying to do before I interrupted myself and ruined the demo? Okay, so you can see we've got a couple of tables there. So the idea here is we have a table called hackathon table, so no originality there. But if you go to your reports, standard reports, and just disk usage by table, you'll see that the actual table isn't there, because that's sort of going to the extents, hobbits, those sorts of things. If, however, we go to our report and do it correctly and go to memory usage by memory optimized objects, you can see that in this particular case, Yes, but we're not taking into account the Victor luck. So now all bets are off because it might be doing some other stuff with this other one. Here's a tip, be careful of what you click on in the GUI. Okay, I don't know if we'll be able to. Okay, so I just wanted to show you this report. Did I click on this report? I thought I did. Reports, memory usage by, well, let's try this one. Memory usage. Okay. What I was trying to do, and I don't know if we'll have time, we'll see how we go. What I wanted to do was show you that both the Hackathon database that's on the SSD and the disk drive have data that's about, I can't remember, 6 gigabytes in size. Okay, and what I wanted to do was stop and restart SQL Server. And you'll see that it takes a bit of a difference to load the Hackathon 6 gigabytes worth of data into the server, because in one case, the Hackathon durability files are on an SSD, whereas in the other case, they're on a disk drive on my laptop. So there's going to be one that loads in 30 seconds and the other one will probably be loading for 5 minutes. It's debatable whether it's ever going to load now. So that's what I was going to demonstrate, but the interests of saving time, I might not be able to do that. But again, please trust me that that is the case. But I just wanted to point out that if you go to your logs, so go to SQL Server logs. It's too good to be true. All the demos were working. Ugh. Okay, so you can see over here, this is the, when I restarted SQL Server, you've got the automatic recovery process happening. But you can see over here that for the Hackathon database that was on the disk drive, you can see at the very top, sorry, it's really hard to read. It's going to say, it's saying something. The analysis was 51,000 milliseconds, and then, well, the undo was a million milliseconds or something like that. Okay, so the idea here is, what I was trying to illustrate is that you can see we've got memory pressures in this particular case. Probably this is better. This is what I'm actually after, okay? This is what should be happening. So sorry, it's because I took things offline. But you can see that in this particular case, it's sort of saying that, you know, it's a 1% complete and we've got another 4,620 seconds to go before that Hackathon table is loaded that is based on the disk drive. Whereas you'll notice over here somewhere for the SSD table, somewhere earlier on possibly, it only took 30 seconds to load. Okay, so you can see in this particular case, it took 31 seconds for that particular table to load. So the tables are the same size, 6 gigabytes, but the one that's based on an SSD obviously is much quicker. So again, just emphasizing that you've got different considerations now with respect to hardware, capacity planning, performance, SLAs, those sorts of things there. So apologies about goofing up the demo. Okay, so never mind. And again, let me just quickly see if I can just retry that report. Let's try a different database maybe. Oh, it's loaded. Yes, of course. Okay. Okay, let's see how we go with this. So over here, you can see the memory usage. So see over here, completely different chart from the memory side of things. So again, you can see the Hackathon table, that's about 6 gigabytes or thereabouts, okay? And the same thing's happening over here. So that's for the SSD. Oh, and that's the SSD. So again, let's go to the other one. Reports, memory usage. And again, roughly the same size. Sorry, it's up here. So 6 gigabytes, 6 gigabytes, so almost identical. So the last thing that I actually wanted to do was restart my SQL Server. So we might as well just quickly do that, which is using this utility. So stop SQL. And restart it. Let me just do a refresh, which is this one over here. Okay, so we're starting up SQL Server. And again, just if we do a refresh over here, no surprises, hopefully. If we expand that out, that you'll see that some databases are effectively unavailable because they're recovering. Okay, so eventually that'll pop up. Eventually. Okay, so as you can see, the SSD is in a recovery, the one that's based on a disk drive is recovering, and possibly if I refresh this, you'll see that the SSD one has been recovered, the other one isn't. It's going to take a substantial while longer because of the hardware that underlies the recovery files there. So let's finish up and maybe come back to that. That's not important. It's as expected. So some frequently asked questions. So just to finish up, no support for partitioning. Okay, this would have been ideal. Okay, so the idea here is what I'm talking about would have been ideal if you could put just the active partition of your database table into Hackathon and the rest of it is disk. And then you just say, okay, switch this out and put it into the disk-based. So Microsoft are aware of this, not in V1, possibly in another version, but we don't sort of natively support partitioning, but you can obviously manually schedule, automate that, those sorts of things there. So you could do that, okay? So this has been mainly designed for OLTP. So a lot of questions got asked of me at TechEd in North America and Europe. We're thinking about ETL. So we want to load things as quickly as possible. I'm not saying no, so it is possible depending on what you want to do. People always come up with creative solutions using technology, but the idea here, it sort of wasn't designed for that. Is designed for short transactions, OLTP environment, multiple threads, multi-core environment. But again, it might work. I'm working with a customer at the moment where we're trying to improve some processes by using Hackathon, so hopefully trying to reduce them from 10 hours, 8 hours down to less than that. Okay, so that's a work in progress at the moment. No support for parallelism. Okay, so again, completely different. Okay, so the idea here is completely different from what you're seeing on the SQL side of this. And this is the not so frequently asked, but interesting or weird question. I'm trying to get a new acronym started on the web. That's my claim to fame. No, this will not be available in SQL Server Express Edition. Okay, so for some reason I got that asked as well. So no, that will not be available in Express Edition. So that's basically it. So we'll have time for some questions, I hope. I'm actually in the process of developing a course on Hackathon, so it'll be close to the availability of RTM product.